So we are looking at the boundary layer flow, and we started out by looking at an integral approach. Okay, we basically look at what does the mass conservation tell us, what does the momentum conservation tell us, and thus we defined a drag force, and we defined that drag force, the force exerted by the plate on the fluid as an integral. So the first integral that you see is what we wrote down. Is that all right? And then we said we do not know what the profile is going to be, but it is a reasonable approximation that we use a parabolic profile for the velocity field, and if so, we can calculate what is the drag force on the plate, okay, or the force exerted by the plate on the fluid. So we said if you take that second expression u as a quadratic expression, that's something that satisfies the boundary condition. That is something that varies quadratically with velocity, with height. So we can use that expression and try to calculate what is the drag force. Okay, so that's where we ended up. So we could continue. We'll first calculate this so-called momentum thickness theta equal to integral 0 to delta u. So we need u by u infinity. So that's 2y by delta minus y square by delta square times 1 minus u by u infinity, that's 1 minus 2y by delta plus y square by delta square dy equal to, you could go ahead, multiply and integrate 2y 2 by delta into y is y square by 2 minus 2 into 2 4 by delta square y square, that's y cube by 3, then plus 2 by delta cube y cube, that's y raised to 4 by 4, minus 1 by delta square y square, that's y cube by 3, and so on. Keep doing all of them and apply your limit and see what you get. 2 by 15 delta. So that's theta. Now we can calculate the wall shear stress tau W as mu into du by dy at y is equal to 0. So that's mu into d by dy of u, that's u infinity into 2y by delta minus y square by delta square at y is equal to 0. So what does that give you? Okay. Why we are writing it down? Because we know tau w in terms of theta. What is the expression? What is the connection between tau w and theta? We derived tau w is equal to rho u square d theta by dx. Okay, and we have gotten tau w now as this. That means 2 mu u infinity divided by delta is equal to rho u infinity d by dx of 2 by 15 delta. So one of them will go away. This is equal to 2 by 15 rho u d delta by dx. Remember, delta is the boundary layer thickness and it changes with x. Therefore, 2 will go. We have 15 mu u infinity by rho u infinity dx is equal to d delta divided by delta. 15 mu by rho infinity dx is equal to d delta by delta, and integrating, going to get 15 mu by rho u infinity into x is equal to ln delta. What is that? Did I make a mistake? Oh, it's that way. So there can't be a log, right? So it's delta d delta integral. That's right. So that's delta square by 2. Yeah, hopefully that's okay. Because we are supposed to get a root, and therefore I get delta equal to 30 rho u infinity x divided by mu square root. Okay. No, there's something else missing. What is that I'm missing? I'm ending with a dimensional quantity equal to a non-dimensional quantity. Okay, no, fine. Yeah. Okay. This x is downstairs, right? So I should be basically doing that. Then I'm okay. So, and therefore I basically have root of 30 times REX. Okay. So this is what we had said when we started talking about boundary layer. This thing that the thickness of the boundary layer grows, okay, with x, and for a laminar boundary layer, it goes approximately as square root of Reynolds x. Okay, so if you assume that the profile is actually parabolic, you basically end up doing that, or end up seeing that. Is that okay? Yeah. Oh, so where should I change? It's 30 by, because I haven't done mu delta by x is equal to x square 13 by rho u infinity x. This is right. So therefore I should really have root 30 divided by root of REX. Is this right? So that we have delta going as x root 30 divided by x u infinity rho by mu to the power of half, and that gives us x to the power of half. Yeah, so the other thing is that, actually as the Reynolds number increases, the boundary layer thickness should go down. Okay, so it has to be a 1 by relation. That also tells, okay, the Reynolds number increases, the thickness goes down. Okay, so that means, see, what we assumed was this is what we assumed for the laminar velocity profile. So if you could write down an expression for the turbulent velocity profile, then you would be able to see how does it actually change in a turbulent boundary layer as well. What was the scaling in turbulent boundary layer? X to the power of 6 by 7 or something, yeah. So you could get that. The other thing is this streamline that we drew the other day. Okay. So that streamline is getting displaced because the fluid below is getting retarded. So that's the argument that we had. Okay. So there is a so how much it gets displaced, this distance. Okay, so it comes at h and it reaches at delta. So that h minus delta minus h is called displacement thickness. So this thing is called displacement thickness. So homework for you, just use these expressions and try to show that delta star by x is equal to 1.83 by square root of Rex, where delta star is the displacement thickness. Just use the equations that we have already written down and try to manipulate to see whether. So you understand what is delta star, right? It's just delta minus h. We know how delta changes with Rex, so see whether you are able to get it. It's a useful expression. Okay, any doubts? So theta is called just the momentum thickness. It's just a measure of the drag force but expressed as a length. Okay, so that's all it is. It's in fact, if you look at it, it's just introduced in this calculation for convenience. Instead of dealing with that particular integral 0 to delta u by this thing, we have just called it theta. And if you look at it, it's basically d by rho b u infinity square. Okay, so that means it's drag force but non-dimensionalized. So that quantity is called theta, but it has the dimensions of length now. Oh, so it's not completely non-dimensionalized. It has the dimensions of length. Delta minus h. So the displacement thickness. It will change with h will not. H is the height in which a fluid element is coming, and it is getting displaced by a distance of delta star. Okay, so what matters is how much it is so delta minus h is what matters. So delta star will be a quantity which will be a function of x. Because it's going to match with the real expressions. Okay, so one thing is that whenever you have laminar flow, okay, confined between two things, it has to if the viscous mechanism is important, like in pipe flow, we typically get something closer to parabolic profile. So here also, if you actually had a complete derivation, you get a profile which is very close to parabolic. So typically, whenever you have flow in very thin sections, it's reasonable. An approximation of a parabolic profile often gives you good results. So that's the only reason. So we could have done the same calculation assuming linear, okay, and you would have gotten a good estimate. Okay, parabolic is slightly better, and because the actual profile is very close to a parabolic profile. And if you want to do turbulent, then you would not want to do parabolic, because you know that it is going to be a much flatter one. So it's basically better to assume something which is like, going to the power of n, where n could be some number which gives you a much more flatter profile. Okay. Okay, so we understand a little bit about how to approach boundary layer and the thickness. We will look at a differential approach now.